Hey guys, Professor Schupak here, back today with another video for you all. In today's video, we're going to talk about dynamic programming. Let's start with an example. So look at this chart right here. It looks really confusing and complicated, but this is summing up a problem that we have. In our problem today, we're a business owner, and we're starting at point A, and our problem is that we want to do a task, call it J. And we have different ways to get from A to J, but each decision we make comes with a cost, and there's different options, and we're trying to figure out, going through all these stages, what's the cheapest cost. So stage one will be, we can go to B, C, or D. From there, stage two is deciding, do we go to E, F, or G. Stage three will be, do we go to H or I. And then lastly, we get to J and solve our problem, and we want to figure out what the minimum cost is. Normally, people think of this problem naively, and we say, okay, well, if we're starting at A, we could go 2, 4, or 3. Obviously, we'd route to go to 2 because it's the cheapest. From B, we could either go 6, 4, or 7, and 4 is the smallest, so we'll go with 4. From there, we have the choice of 6 or 3. 3 is the smallest, so we go to 3. And lastly, when we're at I, we just have 4. So what did that cost us? Well, it took us 2 to get to B, 4 to get to F, 3 to I, 4 to finish. That cost 13. But is 13 the optimal point here? Is this the cheapest route we could take? I mean, it makes sense. Each route we took the shortest and cheapest amount, but it might not always be the case if you think of it naively. And I'll show you why dynamic programming can prove this. So again, we have the chart. Let's start from the end. Let's say that f of x at any point is our cost to finish the problem. We know that if we're already at our goal j, then our cost is 0. We've solved the problem. So f of j will be 0. We also know that in the previous stage, where it could be at either H or I, but all those only have one option. If you're at H, you spend $3, and if you're at I, you spend 4. So if we're at H, we're going to spend 3. F of H is 3, and F of I is 4. Now we're going to do the previous stage. So stage 2, where we're at E, F, or G, and we're deciding to go to H or I. Well, let's assume we were at E. The optimal course of action would be the minimum cost of whether going to H or I. If you go to H, that'll be a cost of 1, and the total cost will be 1 plus F of H. That gives you 4. Or if you go from E to I, you have a cost of 4. 4 plus F of I is 8. So the optimal solution here, if you're at stage E, is you should opt to take the $4 route. And that's the cheapest way to finish your problem if you're at E. Next, we'll try F. The minimum for F, we could either go to H or I. Going to H is a cost of 6 plus F of H, which gives us 9. Or going to I, which would be a cost of 3 plus F of I, which is 7. The cheapest here is obviously 7. So our optimal solution at F of F is 7. Lastly, with G, we can go from G to H at a cost of 3. 3 plus F of H will give us 6. Or we can go from G to I, which would be 3 plus F of I, which gives us 7. The minimum one is 6. So the best solution for F of G is 6. And we're going to write that down to the left here. So now we have this stage. F of E is 4. F of F is 7. F of G is 6. Now we're going to start at stage 1. So F of B, we have the minimum amount to go from B to finish our job. We can spend 7 and go to E. 7 plus F of E will be 11. We can spend 4 to go to F. 4 plus F of S is 11. Or we can go to G. B to go to G is 6. 6 plus F of G is 12. So the minimum cost here is 11. Note that there are two options that both yield 11. And in all intents and purposes for this problem, either one is fine because the idea is minimizing cost. So if you have two solutions that both give you the same minimum cost, both of them are very optimal solutions. You could choose either or given the circumstances here. Next, we'll try C. If we're at stage C, we can spend 3 to E. 3 plus F of E is 7. Or we can go 2 to F. 2 plus F of F is 9. And then lastly, we can go 4 to G. 4 plus F of G is 10. The cheapest, or the minimum here, from 7, 9, and 10 is 7. So F of C is 7. And then lastly, F of D, we can go 4 to E. 4 plus F of E is 8. We can go 1 to F. 1 plus F of F is 8. Or we could go 5 to G. 5 plus F of G is 11. See, again, we have two options here that both yielded us 8. So either one of these courses of actions, given you're at F of D, are both optimal solutions because they yield the minimum costs required to solve this problem. So here, F of D, our cheapest, is 8. We're going to log those. F of B is 11, F of C is 7, and F of D is 8. Now that we calculated every single stage, we're now at stage 0, our beginning, and we can figure out what really is the cheapest way to solve our problem and get from A to J. So again, F of A would be that minimum cost. We have 2 where we can go to B, 4 where we can go to C, or 3 when we get to D. And we know what those costs yield because we already calculated them. So 2 plus F of B will give us 13, 4 plus F of C will give us 11, and 3 plus F of D will give us 11. So the minimum cost here is 11. The cheapest way for us to go from the beginning where we're at to solve problem J at stage J and be done with what we need is $11. which is very different than the 13 we assumed using the naive method. This is why dynamic programming is very important, because it solves the actual minimization and maximization problem and more efficiently and accurately does optimization problems for us. Thank you guys for watching. I hope this example helped you better understand this topic. If you like this video, please like, comment, subscribe, share it with a friend, and let's help as many people as we can. See you guys in the next video.